things gear, we tear things apart, we do some reverse engineering, and lately we design new open source projects involving some form of MIDI. If you've been following along, we've been doing a drop-in replacement board for the Strymon Deco, but more generically the Strymon small box pedals, so that if you have an existing small box Strymon pedal, then you can retrofit it with this to give it MIDI and a whole bunch of other cool things. Last week we added a WIDI module to it to give it WIDI support if you'd like. We'll have probably like an optional pigtail antenna that you can connect to the enclosure and have an antenna there so you get really good reception. And yeah, so we're going to keep going with that. Let me switch over here. So we've been doing some component placement and putting our 3D models together to make sure that everything is going to fit. So the project looks a little something like this, and most of these models have been created from scratch as I wasn't able to find existing step files or 3D models that I was happy with for the enclosure and bits and pieces like that. So it's all been measured sort of by hand. It's not perfect, but it will do well enough. I've added this little cutout here, as you can see from last week, this cutout for the screen connector. So that the ribbon cable can pass through, because we needed a little bit more board real estate to fit all of this external circuitry on, so that we can make sure we've got a really good PCB layout that's going to perform well, rather than having everything squished on there and make our routing and layout a nightmare. So that's the current state of affairs. Now, I just realized as I added this route out here this morning, I accidentally moved this standoff hole from its original location. So I'm going to switch back here to close that, get a bit more space. I need to find, I'm just going to do some Control-Zing to find where that hole originally was. I forgot to lock it in place. Okay, so I moved it. That's frustrating. So I moved it originally from where it was, by just doing a big group move. So not ideal. Hello, if you're just joining in, welcome. Say hi in the comments below. Love to chat with you guys as we do this. What I am going to do is undo so just Control-Z the import of the new file. And I've got this hole where it was originally. We're just going to, hang on, it's not ideal. Check the relative placement, so 30 millimeters from that side hole. So now we can just go back into our board, because I already had the positioning of these pretty down pat. So I'll select that. Now let's turn off violate. So we're going to ignore violators just so I can lay it on here. All right, so it's 25 mil, 42.5. So we'll keep that there. So it's going to be at 12.5, 25. Now, a really helpful hint when you've got mechanical things, or, I use it a lot for parts of the board that relate to external geometries that they can't move because that's a fixed place that they have to be in. We can actually lock those. So I've got a lock here. Now that's going to prevent these from being moved, even if you select them in a group or something like that. We'll go back to the move tool and try and move them, and you can't. It locks them in place, which is really, really helpful. So there we go. But yeah, project's looking quite good. We can go forward again, redo that change, and you can see I've added some fillets or curves to these corners here, so we don't have those sharp internal edges to strengthen our PCB. And then where we've got these sort of internal cutouts, I've added some of those fillets there as well, because the routing bit cannot make a sharp 90-degree angle. It will try, but we're going to make our PCB manufacturer's job a whole lot easier and guarantee that we get back exactly what we submit if we add those in ourselves. Morning, Dan. How you doing, mate? Good to see you. Yes, coffee emoji is on. I've had a long black this morning. I think another one might be due. So yeah, I'm pretty happy with how this is all coming together. It's, some of these tolerances are a little tighter than I would like if I'm being honest. Unfortunately, there's not that much we can do about it. There's really not a whole lot we can do, unfortunately. But like I said, what I think I'll end up doing is making some like laser cut drilling templates. So let's say on the side of your enclosure here, it would come with, if you bought the kit, like a perfectly matched piece of acrylic, just with a couple of like low tack sticky dots. You just sort of put on the side, center it, and it would be perfect. And it would have pre-cut holes, so you could drill your pilot holes exactly where they need to be, and without any fancy, equipment or measuring. You just hand drill, you could get pretty accurate holes for everything. So look, I don't think it's going to be a big issue, but I'll do a test build and we'll see how we go. So today we're going to do more placement and then some routing. So I was hoping to keep this to a 2-layer board. So a 2-layer PCB. If you're new to that, it means that on your PCB, take this ribbon cable off, you have the substrate, so the fiberglass epoxy PCB, the board, and then on either side you have a copper layer which has various tracks and traces that make the electrical connections. Now you can get the most basic board is just a single-sided board, but typically nowadays every PCB house, unless you're doing millions of units in some budget toy, you'll do a double-layer board for your standard $2 or $5 for 5 PCBs, something like that, for like a 100 mil square size. But 4-layer boards have 2 internal layers. They're used for more densely packed layouts, things like that. For example, I'll give you a little early look of this is a working prototype of the upcoming Bridge 1. I don't know if you can see that, but it's quite tiny, has a lot of components packed in there, and there's not enough room to route all the traces in a way that ensure a good electrical connection, follow some basic rules of thumb that we'll be taking a look at as we do the routing in this project. So you need some internal layers so that you've got more space to route your signals, as well as power and ground, which are quite critical, especially when you're looking at high speed or relatively high speed designs like microcontrollers. So that's where things are at. So now I'm pretty happy with the outline of that board and how that's structured. We're going to go, when I'm doing placement and routing, I like to use an imperial grid in mils, MIL, not millimeters, which is 1 mil is 1,000th of an inch. It's also referred to as thou typically. And I like to do that because most of these common component footprints are based on imperial sizes. And it's just, I guess, a bit of a habit. Some people do placement in metric, and that's fine. I despise everything about the imperial measurement system for literally everything else. Apologies for you American viewers and friends. You're great. Your measuring system is not. But it's just a bit of a convention due to the age of some of these processes that's the way it goes. So that's just force a habit. So what we've been doing is just grouping our components together into blocks that make sense to be together. So down here is most of our power supply stuff. I also added an alternate method for power just down here because depending on the actual pedal, I'm not sure if the main board on these differs from model to model that much. Like, it's all really just done in DSP anyway. But so I'm not sure if there's going to be different current limits for the kind of the reference power pin that comes to this board or not. So just in case, I've added some pads so that I can, maybe just connect directly to the DC input, and then there's a separate 5-volt regulator there because the power reference pin on here is 5 volts. So this should be, a fairly low power board, and if we can get away with that, I much prefer to, then we just don't need to populate these parts. But I'd rather have a working board the first time around by accounting for that than, have to wait and send the board away and get it back and so on and so forth. So, yeah, down here is some of our ADC, our analog to digital converter. And if you've been following along, we made that fairly discreetly using some op amps and level shifting transistors. Oh, I don't want to move that board layout because we had some very, not abnormal, but just particular design criteria that couldn't be easily done with just a simple, like PWM, like just a basic RC filter. We had to do some trickery in that. And I didn't want to use a dedicated DAC because DACs are kind of hard to get, and I don't want to design with a specific one if I can help it. Sorry, my nose is really itchy this morning. If I can help it, and then it goes out of stock and we can't manufacture the boards. So, it's a bit of a necessary evil, but it is what it is. Sorry, this is not good viewing. Me blowing my nose. Can't be helped. Joy of a hay fever, suffer a year long round. But alas. All right, let's crack on. So we've got, switching back here, our power sheet. This can still be a little bit, neatened up a little bit if we're being particular, but I'm not being particular right now. So yeah, now it's important to note that you wouldn't be able to use these supplies at the same time. Okay, this isn't the intended use case, because if you connected both of these up, you'd have 5 volts here, then 5 volts there, whilst powering it through here, and you could potentially like backfeed your board, maybe damage the main board. This is a either or, and I don't want to put diodes in due to the power losses and voltage drops associated with them, even Schottky diodes. And I don't want to put anything fancy because there's no need. This is just so that I can test all eventualities of the board with the very first prototype. So here we go. So that's that going on there. So I think that this stuff, because we are going, I've decided that we're going to use a 4-layer board, we get a lot more flexibility with our power routing and management. So all this stuff here is going to sort of go under that cutout. And if we go back to the 3D model and the enclosure, you can see I've actually got there's a decent amount of room still there to be used. So if we need to, we can extend that out even more so to give ourselves a bit more room, which I might do now. We'll just allow for a little bit of extra room. So switching back to a metric grid here. Why am I on 0.5 millimeter? There we go. So I'll just drag it out, another 5 mil should pretty comfortably allow for that. We can go back and measure exactly how much room we have. So from that edge of the PCB to that wall, we've got almost 10 mil. So another 5's not going to hurt at all. It'll just give us a bit more room there. Can always shrink things in later if we like. As a general rule of thumb, I like to try and do as much of my placement as I can with a 25 thou grid. It's not always possible, and in some cases you have to go down to a 12.5 mil grid. I sort of just always halve it in subdivisions. And then I do typically most of my routing with 6.25 thou grid so that I can really make those traces go wherever I want. But that's good enough for now. All right. That's going to go somewhere down there. And most of the, I've already done the placement for the really critical components, which you see here, which is the RP2040 microcontroller, the various decoupling capacitors, our USB termination lines, the crystal oscillator here that's going to provide our clock to the RP2040, the quad SPI, and our various connectors. They're kind of important, as well as the the physical controls and this and that. Everything else can be worked around there. So what else have we got now here? What's that going on there? Q7, Q6. Where are they? Show Q6. Sheet 4. Oh, yeah. Okay. So that's our switch emulation output. So we're using a basically an open drain configuration here. So this is a transistor. It's a FET in this type, an N-channel FET. and we have the source here going to ground. And then we have our gate being controlled by our microcontroller with a current limiting resistor here so that we don't slam the FET too hard and draw too much current from our pin. And then we've got this, this drain here, and this is called open drain because all you can do with this type of configuration is drive the pin low or release it. So when we basically think of this as a switch, when we close the switch, this pin will get tied to ground, which is what the physical switches, the hardware switches are doing, and the foot switches. And then when we open it, this sort of gets left floating. And ideally, there's pull-up resistors already on the control board, but I've added these pull-up resistors here in anyway, just in case. We don't have to populate them on the final design, but it's good to have them there in case we need some stronger pull-up resistors. Two resistors in parallel will always result in a lower resistance. So yeah, just there, just in case. What I might do though is just move these away from each other a little bit, give them a little bit of breathing room. That's better. And I still need to connect up. So there's a separate subboard here, which contains our USB and our TRS jacks. And that is because it's going to be very difficult for, because they're two separate boards, two separate enclosure pieces, we need a way of kind of decoupling the exact location of this from the main board so everything can fit in nicely. So there's a little secondary connector there. You see I don't have 3D models for those, but the black box will do just fine. And then there's a corresponding connector there. Let me see if I can get a better angle of that. You can see it. So yeah, all right, well, that answers my original question where we've got these 2, 3, 4, 5, 6, 7, 8, 10. Why do I have 10 resistors here? There should be 8. So 44, 5, 6, 7. Just trying to work out where those other 2 resistors are from, because it's a little bit strange. All right, so we've got Q9, and it obviously has these two. I'm just teasing this apart into more sub blocks so that I can just really start to make sense of all of these air wires here, as they're called, showing the connections that are yet to be made. And that's going to make things a lot easier to work out where they're all going. Okay, so ADC, so that's our okay, so those 1Ks, I remember now, they're our current limiting resistors for the LED inputs so that we can receive some sort of state-based feedback from the control board as to, what the power up bypass state is or things like that. So, yes. Now, coming back to last week, I actually put those on the inputs of our analog to digital converter here. Where are they? They're somewhere on this schematic. Anyway, I'll find them. Here they are. And I'm doing that because I haven't checked every single pedal, but I want to allow for the eventuality that maybe the LED isn't just on or off. Maybe it's kind of ramping or pulsating or something like that. I want to be able to capture that and use that data somewhere if we decide to use it. So that's why I'm capturing the analog voltage, not just the digital on or off. So they basically are just going into our ADC, but they have to come from here somewhere. So given it has to go up that way anyway, I think that's a reset pin. Where did I just put? Here they go. Hang on, where did those 1K resistors that I was just looking at, where on earth did they go? Am I going blind? Or did I take them up here already? Oh, I put them up here already. Okay, yeah. Because these go right into there, it's a pretty safe place to put them. We'll move them out a bit. So this is where I'm just going to switch to quickly a 12.5 mil thou, I should say. And we're going to put those, somewhere there, let's say. There's no need to do such fine placement yet. Let's say they're going to go about there. and then they can get routed down to that connector. They either should go there or there. It doesn't really matter. That's more out of the way, I think. So let's see, that's kind of nicely broken up. Then this is our foot switch. I've been umming and ahhing where we put these foot switch kind of connectors. If you look at the original board, they're actually quite a big through hole socket. The connectors on them are quite chunky. They're not a nice small JST connector. So I'm wondering, like looking at this, if we might be best off maybe trying to put our power in the middle and then putting room for the switches either side. Rather than going like that, which they do on the original, going like that. I'm thinking that could be the way. And because they are through hole, we could put them on the underside of the board if we wanted to. So now thinking about it, it's going to make, just declutter that space a little bit. So we are going to move that just in the middle there somewhere. I'm going to move these down here so that, in fact, they really should be like there to allow for the connector. I haven't created a specific connector for those, a footprint and model for those connectors yet. I will do it. It's just, I'd rather, just approximate where they need to go and then get this done. So put it, sure, we'll put it there at 1800 and 800, that nice round numbers. Beautiful. Then we can put our power in the middle there. So that's looking good. Happy with that. All righty. So we know that those like switch sort of emulators are going to need to go somewhere. Now, what is important to note is that we can't put big components in front of this connector because our ribbon cable is going to come up through that slot and then fold over to get to that connector. And if you see on the original, we've got some, you don't have, I don't know how well you can see that, but there's not that much clearance. Now, there will be enough room for us to put some passive components like these, small resistors and transistors and things like that. They don't take up much height at all. This resistor is like less than a millimeter high. I'd say that's a capacitor, actually. The resistors are even smaller. They're not very tall at all, so we can probably put those in there somewhere to get them out of the way. That could be good. We'll just have to see. And then I'm going to put this DAC circuitry up here somewhere along with these op amps. Yeah. All right. C39. What's C39 doing? Is that from our power? Ah, there it is. Okay, so it needs to be in with the 3.3 volt regulator. It just fell off somewhere there. C41, C37. Let's make sure they're not part of this as well. Oh, they're our output capacitors. Okay, sure. Well, we need to make sure we keep those in there with the 3.3 volt regulator. And the idea is just to have no loose floating components that don't have a spot anywhere. That's going to be part of our DAC. This is our serial wide debug connector. It is a pretty low speed, like 400 kilohertz signal. It's not very fast at all and doesn't require tight timing. So the rising and falling edges are not particularly fast. So it's going to go out of the way somewhere along with our reset switch, I think. And we'll just deal with running those traces across there. Yeah, so the PWM signals that drive our DAC come from these pins here. So we're going to need to sort of probably route them through and drop them down onto a lower layer, so we don't interrupt this crystal here, because we want to just have nothing but reference. We don't want to have any signals running across there. So they're probably going to come down there. So these op amps, they'll be floating around there somewhere. And they are rail-to-rail op amps, fairly, jelly bean rail-to-rail op amps, bit of reasonable performance. Right, then we've got some stray decoupling caps here, 59, 60, and 61. Where are they to be found? Show C59. We're on gate 3. They are... Oh, okay. So they are... Great. They're the decoupling capacitors for our op amps. So I need to keep those over there. All right. I've got the supporting components for our... what's it called? For the MIDI module. And like I said, I've only got the currently the model for the version with the onboard. I mean, it's sort of it's a bit of a generic module actually, onboard antenna. The one we're going to be using has an SMA connector for an external antenna, whereas you can see on the Bridge 1 board here, it's actually got a PCB trace antenna. And the reason for that is we don't want to have to, it's going to be pretty difficult for the average DIY, or really the non-average DIY. It's quite difficult to cut a nice, clean, precise slot, and you don't want to mangle the top surface of your pedal. So if you use an external antenna, you can just have a hole on the side next to these for a little pigtail connector to run your antenna to. You have a little external antenna there. So we've just got some supporting circuitry for that. An RGB LED. I'm probably going to use a bigger RGB LED than this one, I'd say. Although, yeah, it's mostly just like a status indicator while you're working on the board. It might be fine. But just some basic decoupling for this. And then some test points for programming and verifying the actual module, because it needs firmware uploaded to that as well. So let me move those out of the way a bit. Then we've got some test points here. I'm going to add some more test points as we go to various parts of this that we might want to expose for testing and validation and things like that. The question is, I guess, do we add test points to the top or the bottom of the board? There's advantages and disadvantages to both. If we have them on the top, then most of our signals are going to be routed on this top layer, which is nice because then we don't have to, our test points are on the same layer as most of the traces, but they are going to take up space, and we're going to need to allow room around them for a test probe or a multimeter probe to get into there. Whereas on the bottom, you can just sort of put them wherever, but then we have to add vias for all of them and break up our planes a bit more, which I don't want to do. I think we're going to have enough room to do them on the top layer. So yeah, I'm just going to go ahead and add these to, I'm going to go to all right, so I haven't placed that cleanly on the grid. So I'm just going to add these, next to the pins that they are going to be connected to, so we can, one, get them out of the way and actually get the right positions for them. I'm going to add them fairly close. These are sort of use once type kind of operators. Something like that. Do that. That's a bit annoying. I guess we'll sort of just equally space those out a little bit. Oh, hang on. What am I doing? Just trying to make them sort of symmetrical, I guess. Then can go there. And this is just going to really start to declutter our board layout so we can make sense of what we're doing a little bit easier. We'll do the test. These boards are going to get tested before we solder the pots onto them. So I'm just going to give them a little bit more breathing room from each other to allow for that. Make that a bit easier. Okay. This one's a bit tricky. It's not going to be able to go nicely in line with the pin, so we'll just put it there for now. And these are our JTAG connectors for programming the module. So that all looks pretty good. Then we've got this jumper for selecting the board rate there. it can just go. There's nothing, you can see none of these pins here are connected, so it can just go there. It's not really of much consequence. Then these are, there's some resistors for our indicator LED. I don't really know where this LED is going to go. It's whether it even gets placed in the end. It'd be nice for some testing and debugging purposes on there, I think. I'm certainly not going to bother putting it on like an external, visibility on a light pipe or something. The data for that is getting fed into the microcontroller anyway by the status pins, so we can use these other LEDs. But it'd be nice to have this on board. Oh, sorry, I'm just a bit of a brain dead moment. So these, all right. So sorry about that. Completely spaced out. Those resistors go there. There's not much happening up the top here. We'll probably accept that we'll route those up and under somewhere there. Move these, just decoupling and filtering down to there, something like that. So we'll put these somewhere here, I'd say. Current limiting resistors for LEDs. They're just some 220 is just a value I picked at random. We might want to fine tune them to get more match brightness. Good morning. If you're just tuning in, welcome. Say hi down in the comments. And if you guys are working on a particular project, something of interest, this channel is all about DIY projects and open sourcing things. And if you have ideas, if you're looking at this or you have a question, feel free to ask questions and I'll answer them as best I can. Or if you have some input, something I've missed or a design suggestion, please let me know. Are you working on any projects at the moment, Dan? Do you have anything fun going on lately? I know you've had a couple of cool sort of just, couple of cool things sitting on your board there. So these decoupling capacitors go to pin 10. I'm pretty sure that's the actual power input pin. Let me check. Yeah, pin 10. So as sort of usual best practice, I've got the 100 nanofarad capacitor nice and close there, and then this larger bulk 4.7 micros somewhere else. So while I'm doing this, I'm going to be control clicking. If you're not sure, when you control and left click on a component, it snaps it to the grid. So I want to make sure that everything's snapped to this placement grid that I'm using. And I'm going to do it. I'm going to move these like this, like so. Oh, that might be getting a little bit dicey, I think. So that I can get them nice and close to those power and ground pins. But that is getting awfully close. Oh, hang on. No, those pots don't even sit flush to the board. That's fine. Totally fine. Fine, totally fine. Yeah, that'll be nice. They're nice and probably just a little bit of breathing space. There we go. So, all right, this is better. And that's decoupling for that LED. Cool. That is decoupling and filtering for that pot so that we get as much of a nice smooth analog waveform as possible. Cool. In fact, that's probably going to be going down there, I'd say. So I'll put it there. This reset switch, so that's decoupling for that LED. We'll chuck it there. Can probably go in there. Oh no, that's our boot mode selector switch, which is part of this quad spy little sub block there. It's probably going to go somewhere in here, I'd say. Somewhere in there, or maybe even here. Yeah, that's fine. Then we've got our switch emulation. We've got some debouncing filtering for our foot switch there. Some more foot switch filtering there. So it's going to be nice and close to that. Dan, I just finished up the GitHub repo for my MIDI looper. It's pretty basic, but the code and schematic is available for people to look at. I'm not a programmer, though. I kind of learned as I was going. Hey, yeah, learning as you're going with projects. It's how I got started with, electronics and firmware development. Learning as you go, highly, highly recommended. I think different people have different learning styles, but, for one reason or another, project-based hands-on learning is the way that I think most people who go down the engineering or maker or development sort of role really learn best. Chuck a link in the chat, Dan. You should be able to do that. Not sure there's any permission issue with like posting a link in there, even via Facebook. But yeah, chuck a link in there for people to check out for sure. If you want to, of course. If you don't want to, you're still working on stuff, then no pressure at all. Okay, cool. Well, 72, 73, are they output caps for their 5 volts? 72. Oh, input and output. Okay. Okay, so that 73 is the output for our 5-volt regulator. So it's going to be going down here. And input's going to be going here. Somewhere there. Cool. Bananas. We can actually simplify this a lot. We don't need... I suppose it would be helpful. Yeah. Never mind, because this is an either-or kind of situation. All right, let's go quick save on this. Just get in the habit of saving your work as often as possible. Okay, so apart from that mess, which I'm going to want to place out, I don't want to just chuck it on there because it's going to really get in, clutter over the top of some things. This is looking pretty good. So what I might start doing is a little bit more careful placement of the things that I'm, happy with where they're going to go. And then, yeah, we'll go from there. So I know I'm looking at it. There's nothing else really that I want to put in there. This is nice and low. We can't put any of those electrolytic caps across there because there'd be issues with the ribbon cable. But let's get started. So I'm going to switch back to the 25,000 grid. All right, so that is going there. Then where's our... Just going to start placing these resistors, roughly in position so I know which pins they're going to. Looking at this board, you could probably get away with a 2-layer design, two-layer board layout. But it's not going to add that much cost, which is the main reason why you would go with a 2-layer over a 4-layer. It's not going to add that much cost, and it could be, a really good design consideration if you've done a 2-layer board, because the jump from a 2-layer board to a 4-layer board can be really daunting. I get that, because you go from a 2-layer board, you get your board back and you can see everything. You can, cut traces. Everything is accessible. It's just top and bottom. Whereas a 4-layer board, there's stuff inside that you can't get to. You can't see if you've made a mistake somewhere and your clearances are too low, or you've, connected something up incorrectly. You can only really probe around and reference back to your schematic, and maybe hope your PCB manufacturer hasn't stuffed up somewhere. So it can be really daunting for sure. So this might be a good process to show people going to a 4-layer design. Cool. So that's sort of the pins that those each of these are going to go to, and we'll just find a bit of a generic. I like to sort of find a pattern when you've got these repeated sections or repeated little, component topologies. I like to try and find a placement pattern that works well for them, and then try and copy it, for all the other times that I'm using that, really. So as long as it makes sense, I think it's a really nice, way to go about your designs, and you can play around with it and tweak the placement of things to try and make it smaller. Something I am going to do now, having decided to move to a 4-layer board, is we're going to have a 3.3 volts on one of our internal layers. So I'm going to go air wires hidden, because I'm actually going to be doing the routing on our inner layers, and it just declutters all of this a little bit. I've already done that with my ground, so you can see it just really simplified things a bit there. I'll get to PCB layer stack up. PCB stack up on layers a little bit. I'm not going to touch on it too much, but what stack up means is if you have 4 layers, the stack up is what you put on those layers and also how the physical board is constructed. So for example, we're going to go to the JLC PCB website and take a look at some of their stack up here. And we're not going to be doing anything fancy. Typically when you're talking about stack up, why's that gone blank? Hang on, let me try and... There we go. When you talk about stack up, you're talking about controlled impedance and things like that. Not so much. We're not really going to be doing anything like that. I'm just trying to show you, to illustrate the point. So on a 4-layer controlled impedance stack up, you get, 0.03 millimeters of copper on top, then this pre-preg layer of 0.2 millimeters, then copper, then this internal core, then copper, then pre-preg, then copper. And so the core and the pre-preg are like non-conductive layers, and then obviously your copper is. And so you can get different stack ups that give you different, you can see different thicknesses and different impedance options depending on what you're designing. But all we're really going to do is be using those layers. One's going to be a ground plane and one's going to be a 3.3 volt plane. If you're interested in learning more on this, a YouTube channel, Phil's Lab, which I highly recommend for anyone wanting to get into, this space, and in particular more. He does a lot of stuff with DSP and higher end PCB layout and routing. He has a really good video on EMI, like EMI design considerations for PCB layout. And he talks about PCB stack up and the importance of it and where you might want to consider it or not. So after this is done, I'll leave a link to that. But I digress. You can see quite simply, we'll go to our design rules. Oh, this pop-up window doesn't show up. Sorry, but I've just gone to the DRC, which is design rule check, and I'm going to load a 4-layer design rule. JLC, was there JLC 4-layer? There we go. That's good enough. So you can't see the layer stack that I'm trying to show you. Okay, well that's a bit of a shame, but never mind. Yeah, so we're going to have signals on our top and our bottom layers. If anyone is interested, Dan, if anyone's interested, yeah, absolutely. Just drop a link in the chat. I didn't see a link come through. Maybe you posted it. Let me check on the Facebook post. Hang on. No, don't play my video on top of me. That's gonna be ugly. All right, well, let me mute that. Yeah, sorry. Let me know if you tried to post a link. It's auto playing again. Let me know if you did try and post a link and it didn't work, Dan, because there we go. Yeah, there we go. So let me. So there's the link. I just popped it up on the screen there if anyone's interested in checking out Dan's project. He put a post up in our user group. Let me, and it's just a really nice kind of bypass looper and switcher built in, really good DIY project if you're interested in something a bit more advanced. I did a similar one in the same format enclosure with 8 switches a while back, and it's a really fun project. Maybe we might, I'd love to maybe, we could collaborate or sell it as a kit or something down the line if there's enough interest. Definitely open to doing that. But yeah, go and check it out if you are interested. Cool. So let's get back to PCB layout. There's a nice little side note about our stack up, but basically we're going to have signals on the top and bottom layers, our outer layers, and then our internal layers we're going to use as a 3.3 volt power reference plane and then a ground plane. And that's not the ideal solution for really high speed signals. Ideally, you have a ground plane adjacent to every signal layer. It's really not going to matter in this context. It's going to be totally fine. If you wanted to get really finicky about it, the way that you would do it is have your depending on your stack up, I believe you would want to have your outer planes as ground or your inner planes, either other, but ideally your, basically have 2 ground planes, then 2 signal planes next to each of those ground planes, and then you route your power separately. So back to it. I'd really like to position this so that I can just kind of minimize the board usage here, but it's going to start getting a bit cramped. What I might do is I can probably move that connector or the cable slot down a bit. I don't see that being a big problem. That gives a bit more breathing room, just down 1 millimeter. Go to 12.5 thou grid, and that should give me enough room to sort of place these resistors in a sort of pleasing aesthetic configuration, I guess. Something like that. Something like that. It gives me a bit of room away from that edge, a bit of room away from that connector. That's good. I think that's fine. I kind of like the way that's laid out. So we're going to bring everything else over. Cool. And then this resistor, I'm just sort of, going to take that little layout and mirror and match it to everything else. And that pin, of course, is going to go to our microcontroller, which I don't think I've actually put pins on yet. That's a good point. Yeah, I've got no pins for that. So that's probably, rather important to have. Would have been a bit of an oversight. So that's that. These pins here are the inputs for the physical switches, but then we need the outputs to drive those transistors to the control board. So that's going to the connector. So ideally, I want to see if there's some free pins along this bottom edge. That'd be really nice. What have I got? 18, 19, 13, and 4. The power pins. Anything along here? What I might do for starters, I'm just going to do a bit of pin rearrangement, because a lot of these pins, it doesn't actually matter where they are. So these toggle pins are going up here. So if I can move them up to here somewhere, there's 2 spare pins, then I can use those pins closer to this connector to be a bit more useful and make my routing a whole bunch easier. So what are they? Toggle is 17 and 16, and I want to put them up on like 28, 27. So what's on there? I was trying to avoid using the ADC pins, and then it just was really unavoidable. Okay, so 20, 27, 28. Whether I need to swap these around to make the routing a bit neater, I don't know, but toggle A. I do really like this feature they just added in Fusion, where if you're renaming signals, it sort of can show you autofill options and things like that. It's quite nice. Now we can get rid of those signals from there. And now that's going to save us a whole bunch of headache. We've got these pins free to use down here. I'm actually going to take this opportunity to try and do, take the same approach. I'm not sure if there's much more optimization I can do with that. We'll probably just cross that bridge as we get there. But certainly, I think if I bring FS1 over to pin 8, because it needs to go down here, that's going to make a bit of a difference. And this is stuff you can't really do when you're just in the schematic. You really need to see the board layout and get your components in place to see, what optimization, what changes can be made. But yeah, okay, cool. So that's there. Now I could use like 9, 13, 14, bump that up 15 for those pins there. That's going to be quite nice, I think. Let's do that. And if we want to swap some things around further down the track, then we can. So 9, I'm going to check the order here. I want 9 to be that one there, which is going to be FS1, sorry, FSL signal. That's pin 9. It's going to be FSL sig. All right, nice. Then that next one, just 13. So 13, 14, 15 are going to be then what's next? FS, so the FSR or FS2, then toggle, what's next? Toggle B, then toggle A. Okay, in that order. So then here, here, and here. Now I'm going to swap FS2 to this pin here. That's going to become toggle A sig. Well, that's a bit tight. Toggle B sig. Why is that not the right? Why is that not the right pin name there? What have I done differently? Toggle A sig. Oh, toggle underscore. Okay, right. So I've just sort of misnamed that pin according to my little convention. There we go. And then that is going to be FSR sig. Cool. So now when we go back, welcome if you're just joining in. Feel free to say hi in the chat. Let me know if you're up to any interesting projects or if you have questions about anything. I want this to be as interactive as possible. So if you do have questions or want to know something or have something you want to chip into the design, then leave it in the comments. All right. That's looking pretty good to me. Certainly much needed because none of those pins I can't move those. I can't really do anything about where they are. Unfortunately, I could use like the programmable IO and put the make a spy on the other side. I really don't want to do that. I just want to, don't want to muck around with that as much as I can help it because it's just going to chew up time at the end of the day. I'm going to see if there's any connections running across here that I could. So the PWM can go on any pin, but they are going across to the DAC here. So moving them from here to there isn't going to make much difference. Everything else is, I guess, pretty well, about as well optimized as it can get. I would say. What is that pin there? Is that 13? Oh, sorry, what's that net? I should say, not a pin. Here. Oh, okay. So that's right. Yeah, I remember. That's part of the VREG decoupling. It's just interesting that it's not. I wonder if I've messed up the placement of that because there's no pin that it's connecting to anywhere near here. Yeah, that's kind of frustrating. I'm going to go to the Raspberry Pi hardware design sheet and just take a look at the power that they suggest, because that'll let me know if I've done anything silly fairly quickly. So jump over to here. Hopefully you guys can see that. Let's make it a bit bigger. So there's 23 and 45 and 50 are all connected here with appropriate decoupling, and then they have some notes of some kind of what's the word? Just allowances they had to make because of the physical size. The decoupling capacitors here, yeah. I'm pretty sure they missed a couple. So pins 48 and 49 share a single capacitor. Internal voltage regulator. This is what we're interested in here. Looking at, can you kind of close that? Okay, there we go. Okay, So 1 microfarad on, okay, on pins, VREG in, VREG out. I just want to make sure I haven't done anything silly. Missed something in here. VREG out and VREG in, I guess. So pin 44 and pin 45 have to have those 1 microfarad as close to them as possible. And I went through this and I'm fairly sure I did that. But so USB termination resistors. Let's say 44 and 45 are here. 44. Okay, yep. So I've got 1 microfarad there, 1 microfarad there, for sure. So I've pretty much done that. It's 13. Just trying to work out what that extra. So 23, 50, and 44. So pin 50 is down there, and then 23. I think so. I think what's happened is I've mixed up my 100 nanofarad, and so where's pin 23? It's here. I dare say that. So pin 22 is just a regular I/O power pin. That's part of our crystal oscillator network. There's no power pins down. Oh, pin 10. Of course. So, that's going to pin 1. Then we need 1 on pin 10. And it's just strange that I've sort of messed up that decoupling capacitor for that one there. Apologies. Just trying to work out what on earth. I just want to make sure I've got this right. Better to guess and check now than later. I can't. I mean, I could, flip this way to get this in closer. I just want to steer clear of this crystal oscillator if I can help it. It's not too bad. What I might do is I'm going to move this crystal oscillator down here a bit and away. And I want to make sure I keep lots of distance between this oscillator and this sensitive analog circuitry here. That's for sure. Now that can go there. It's going to have to come up through there. Look, it's not ideal, but few things in life ever are, and I'm not sure if there's much better alternative. Maybe just give that a bit of space from that decoupling, keep those high energy traces away. Yeah, that's better. Okay, now I've got a little bit of breathing room for that decoupling, because that's going to be pretty important. All right. Some of this can probably be moved a bit closer. I'll sort of shrink everything in and condense it a bit more once I've got all the component placement. We can really start to optimize the layout. It's worth just taking the time to do this. It's going to make the routing so much easier. But after, where were we? We were placing these. So let's get back to the task at hand. Getting all these components in place. Probably gonna have to move everything over a bit to fit that last transistor in. Let's say they look nice and evenly spaced. Now you might think that it's just sort of nitpicking and personal preference as to trying to lay everything out cleanly, and to an extent it is. You can spend a lot of time really nitpicking over your design, and you can actually waste a lot of time with things that aren't important. But things that are important, a clean layout that is, easy to look at and see what's going on, not only is nice, but it also is going to make it so much easier for other people to look at the board. And because I'm designing this for other people to be looking at and understanding, I want to make it as well laid out as possible so that people can follow along. I'm going to center these around those resistors. Makes debugging easier if you're trying to catch an issue. It makes that whole process a lot more straightforward. There's a lot of reason to spend some time just really making sure you've got a well, nice clean layout, and that's nice. Okay, this DAC here is big kind of hot mess. I'm just going to export this to the 3D model. I like to do this every now and again. Just I find it helps me keep my perspective as to where things are actually at, and visually making sure I've got enough clearances. It's really easy to get lost in the 2D PCB layout world and not kind of ground yourself with where components are actually going because you're working on such a small scale. It's just something I find helpful. Yeah, so that's looking quite nice. Obviously, I'll need to go and tidy up the silk screen a bit, but yeah, that's pretty good. Everything's looking all right, I think. Just give me a second. An electrician has rocked up to put another exhaust fan in. I will be back in a minute. Oh, Sam. Hi, mate. Sam, is it? Yeah, Sam. How you doing? Yeah, nice to meet you. Yeah, come through here, mate. It's right at the back. Yeah. Yeah, part of it. Like one tree was the exhaust fan. Right up back in front of the house. I'm just in this room working. Do you need anything from me? No. Okay. I'll just stay out and. Too easy. Just call out if you do, mate. Yeah. All right. Sorry about that. I left my glasses in another room, so costume change. I've got really bad ventilation in one of our bathrooms. It's just like the house is kind of narrowish but quite long, and so the back bathroom is right at the back of the house, and there's just this one really weak ventilation fan that then is ducted right to the front of the house, and it just does not cope at all. Just look at these. I might have to check these footprints because they're a little bit. This is a little bit off on this. I don't know if it's the 3D model. One second. Sorry, mate. Yeah, manholes in the garage. It's a bit of a tight fit. It's a workshop in here. So there's something dumped in it. That's an exhaust fan for the lace car. Okay, right. I'm just going to go and grab my torch. said, just in here, so just knock on the door if you need something. And we're back. Sorry about that. Original glasses are back. So, yeah, I'm not sure if it's the pads or the 3D model. I suspect it's a 3D model, but we'll take a look. So, how's that PCB coming along? Good. It's going to leave that there because, like I said, a bit of a hot mess. Now, we've got this decoupling for our LED. I'm going to try and leave that there. It's a little close to the edge. That's not ideal. Usually you want to try and avoid that. So I guess if we can, we will. This is probably going to come up here because then we can, put our switch somewhere like that. Maybe get that away from the edge a little bit. Not really ideal. We can probably just put it there. That's going to be nice and out of the way. We can have our switch there with a bit of space around it, or even bring those. Yeah, bring that guy there. Something like that will probably work quite well. All right, then we've got the decoupling for our LED up here. So I want to check that there should be plenty of room to have a cap under that potential under there. Yeah, plenty of room. So we can actually mount a lot of our passive components underneath there to make it nice and neat. All right. Cool. Then if we go back to the schematic, if you're not sure what's going on with this potentiometer here, basically got a capacitor here, which is sort of like a localized decoupling capacitor, but just to help smooth out any ripples or noise that might be on that pin at that point. Yeah, so it might be on that pin at that point. And then we've got this RC filter just acting as a low pass filter. And the exact values of these, like 221 microfarads, pretty common. That's going to give us a decent response on the pots. We might need to lower this resistor value a bit there. It's more of a placeholder, and we can just experiment and look at. But if we go to I find it, oh wow, what a mess. I find it really hard to type and talk at the same time. No, not this one here. If we look at the response of this filter, let's see, yeah, so we've got a cutoff frequency of 723 hertz on the Bodhi plot. That's going to be more than enough. It's not going to introduce any lag as we're turning the pot. So I think that value is going to be fine. I don't see it being too much of a hassle. Let's return back to here. So this is our series resistor there. And then let's go into the filter cap there. And we want to filter right at that supply voltage there. And then those grounds are nice and close. So that arrangement works pretty well for me. Again, we've got our decoupling LED. Make sure I'm giving them sort of the same amount of space. Let's go. I'm just trying to work out. So it's going into ADC. So we want to run these signals this way this time so that everything's nice and neat. Then again, we'll put this decoupling cap right close to that pin to filter out noise. Cool. We're just going to go ahead and rinse and repeat for all of this, really. LED decoupling cap, then filter, and away we go. This time we're going to come out to the left here again. I think so that we're not getting too cramped and squished. And there. Cool. And that's sort of looking fairly similar to there. Yeah, move that. Actually, I wanted to keep that aligned horizontally. Yeah, cool. Okay, sweet. Let's go through and do that for these other two. There's that decoupling cap. And again, I'm just going to route them out to the side that makes the most sense. Probably just tweak and change that so it's nicely aligned. But yeah. So what was the Dan? What was the original inspiration for the Grelbatron? You just sort of wanted to have a go at it, something like that. Did you have much experience in projects like that before? What's that? C9. Check which one that is. Okay, yes, that is in fact the filter for that. There. All right, you can probably hear the electrician walking through the roof there. All right. Position that there. So just trying to copy the same component placement as much as I can, just to keep things nice and consistent where possible. That cap's going to go there. I actually think I'm going to change. I'm going to put this where possible. I'm going to put these caps here external to the pots. I think it's going to be a little bit neater. And then I've got nice access to sort of route it to the 3.3 volt and the ground pins. Okay. So I'll do it. What was I doing it like that? No, one. Yeah. There we go. Cool. Let's give that a quick save. Now, with everything, just jumping back to I'm going to generate our 3D model. Again, actually, there's no really need to regenerate that model, but, this is all starting to look a lot tidier. Things are going to be really easy to route. Our placement's not going to be too, cramped. What the decoupling for those op amps. I'm just going to check which one. It doesn't really matter. If you look at our schematic, they're all connected to the same, voltages, but for neatness sake, I want to make sure that C59 is next to IC1 and so on and so forth. So they just sort of increment together. C59, IC1, C60 will be IC2, and C61 will be IC3. Very good. Then what's that? C42. Yep.
What I had planned on doing, I'm not going to do.
Yep.
Because all I quoted on was just putting a 250 mil exhaust, like just a big round one.
Yeah.
Above it. I'm not going to do that. I just don't think it's going to work properly.
Sure.
I'll speak to the owner and the real estate. I'm going to opt for it's a smaller hole. The suction on it is a hell of a lot better.
Yep.
But it costs a lot more. So I'm going to go back. Now that I know I'm looking at.
Yeah.
I'll do another price up. I reckon he's going to approve it because he's going to have to do something in there. That's just shocking on that design.
That's the thing. Well, it still's moved in, and it's so even with the window sort of open and the fan on.
Yeah, it's this far away from the shower head.
And you can see the steam. It's literally next to the fan.
Yeah.
And it's
even when I put this fan in, I'm going to tell you I'm not 100% going to guarantee that it's going to work. It's just. You know what it's like. You get in there, it's steamy. Like it's this far away.
Yeah. And he only came out and had a look at it the first time.
Yep.
And he saw that there was a whole bunch of insulation bagging that had just been placed right on top of the vent too.
Okay. Yeah.
Sounds like there's a hot mess of it.
Yeah. I'd shock it up there. But I think I know what I was going to do. Definitely not going to work, so I ain't going to do it. It's just going to waste my time, his money. So I'll get back to him, and yeah, too easy.
Well,
Hopefully, I can get back here later this week.
Yeah,
Or next week. It'll just depend on how quickly they approve it.
Yeah, well, I work from home, so pretty much any day during the week. There's a couple of hours which are no good, but most of the time it's pretty flexible.
Yeah,
so.
sweet. No, too easy.
All right.
Hey, no worries. Get you later and get out of here.
No worries. Hey, mate.
Hang on, you're late. Come here.
Take your comfort stuff, mate.
He's jumping in some muddy puddles. I
Yeah,
do
I'll
not
bet.
go on the carpet with him.
Yeah, but John, I'm just giving you let you know when you're coming through. Pretty much, I'm like between 8 and 5 is
Easy.
works well for me.
So perfect.
No worries.
Too easy, mate. I'll see you hopefully soon.
Yeah, see you, mate. All right, sorry again, folks. Electrician, lovely guy. All sorted now. So we're back to a PCB layout. I'm trying to work out what that is. What's C42? It's okay. That's decouple. All right, so that's decoupling for our ADC, and I just forgot to move it. So 62, 63. 42 and 44, which will be, I'll bet, all those. Yeah, so that all needs to be with our ADC up here. Cool. And then that's debouncing or filtering for our toggle switch. Cool. I've only put 1Ks on those toggle switches by the looks of it. Might up that to 5K, I think. I'm going to go to our resistor library here. 5K, some sort of preset values that I made there to make the bomb export a bit easier. It's going to give us a little bit better debouncing on that. Cool. So that's all looking pretty good. It might seem like I'm being, it's a bit tedious and, you could do this much quicker. You certainly could just chuck things sort of a bit willy-nilly. And it'd probably work just fine. One, just kind of, don't do a crap job if you don't have to. But two, like I said, there's a lot of very real, benefits other than aesthetics to really take your time and do a good job on your layout. It's going to save you a whole bunch of time in the long run. And it's also going to save anyone trying to understand your work a whole bunch of time. And also we'll make sure that we get, really good performance out of our board. That's a very real factor. So cool. Yeah, nicely aligned up there. Liking where everything is. Yeah, this serial wire debug there, it's not ideal, but it's, those pins are probably going to have to drop to a bottom layer or something, come out there, avoid that nonsense and land somewhere here. Can't really be helped, but like I said, it's pretty low priority signal. It's only used for programming and debugging, so not too concerned. I will move that resistor out of the way there to match the other LED. Our power is going to be somewhere in there, so that's nice. What we might do is lay out our power section now. So that's going to be going in here. I'm going to, I think, double check the length of these physical connectors to make sure I am allowing enough room from the pin. So the whole, the silk screen that they've got there is 15 mil by 5. So as long as we add enough of a box there, what I might do is make just a bit of a, probably don't really need to worry too much, but it'd be nice to, align these with a metric grid and then just draw a bit of a bounding box so I don't have to keep worrying about. Actually, hang on, no, what am I doing? Because they're going to be on the bottom side of the board. So all I need to do is measure that. So 46 to 60. So going to need to be right up there, but plenty of room. So we'll go back to our imperial grid. So if we put that, there, that's going to allow for plenty of room, I think, and then we can put these components on top there if we're putting that on the bottom, because there is enough clearance. If you look at the way this is constructed, it goes like that. I don't know how well you can see that, but there's certainly enough room for those connectors under there. Yeah, that's going to be fine. It's going to be fine. I'm thinking maybe I should put them on the top to just keep it consistent with the original design. I'm thinking I might actually do that. I'm chopping and changing a bit here, but it would just make it nice and consistent with the original design. I think that's going to be enough room for that connector. I'm going to double check. 0.5, so what's that? It's about, 20.5, so only needs to be 5 mil. Yeah, that'll be plenty.
Oh, really?
Cool. Okay. What I'm going to do is rotate it so that the signal pin is close to this side, so I can connect these filter components a bit more easily. Lovely. Lovely, lovely. Get those out of the way. Now, where's that? That's at like 17. So I just moved it up by that much. And then put these ones on top, I think. That's going to lay out quite nicely. We'll snap that to the grid. There we go. Cool. All right. It's coming along well. Yeah, before we finish that, I'd like to route this power out. So let's have a look. So power's coming from that pin V in there. So that can kind of come down to here. So our power input's going to be somewhere in this vicinity, I think. And we'll try and flow sort of from left to right. I think that's what's probably going to work well. So let's separate. I'm going to go to our 12.5 thou grid here because I want to make sure I get these decoupling caps nice and close. So 5 volt input is going to be somewhere here. Then we've got some filtering just with a ferrite bead and some bulk storage capacitors. So it's going to be going to the input there. Hang on. V in. How am I doing this? All over the place. 5 volts there. I'll have that V in. Yeah, it's probably going to have to be, in fact, down there. And then our so something like that, and then we'll have that ferrite bead in the middle there, nice and symmetric. And that V in, I want to put that really close to that power pin to just filter out some extra noise and be nice and localized to where the power is actually coming into the board where possible. So I can go somewhere there. Lovely. That needs to rotate. Cool. Move that down just to give it a bit of separation. It's going to be a little bit better. Move away from those big electrolytics. Cool. Then our output caps. We're just 3741. They're the output caps for 3.3 volt regulator. And again, we're always putting the lowest value capacitance closest to the pin in question. This is good practice. I'm going to put those nice and tight there. And this is the way I like to lay out these SOT 23.5 packages. This is an enable pin, so I generally route the power into there nice and close. a thin trace of the enable pin to there, so I can have a nice, uninterrupted ground connection, and then route the output there, and then usually just drop some vias for those down to the bottom layer, and it works quite well. And then our bulk storage capacitor is going to go somewhere there. Can really shrink some of this board outline down a bit in hindsight. In fact, this can probably, if we move all of this over, it's going to be a lot closer to where that power input is coming. I can move that away. And then do that. Bueno can go somewhere there. The placement of these smaller capacitors is a lot more important than the bigger capacitors. Basically, the lower the capacitance value, the more it's going to be affected by how far away it is from what it's decoupling, because those traces are going to have parasitic inductances, most importantly. So generally speaking, the impedance is a lot more critical because it's the same value of impedance or inductance, whatever it is that you're trying to minimize, is going to quickly dwarf a really low value capacitance than it will a high value capacitance. These bulk storage capacitors aren't really critical in terms of their placement, but we can't put them in there because we decided we might put our what's called foot switch connectors on the top side. Move that down a bit just to preserve some space, and we can put that guy there somewhere. I think that seems good. Then I'm going to take the same left to actually no, I'm going to take the opposite approach of left to right, because then I can route our 5 volts right up to there. So this one's going to go sort of this right to left, just to make our layout a little bit easier. Or no, actually, it's not going to be the end of the world. I'd just personally like to keep a sort of nice symmetrical layout if I can help it. I think that's going to make understanding the power section and what's going on a bit easier. And yeah, that's the way we're going to do it. That's going to go to there, which becomes our filtered voltage. I'm actually going to match these so they line up in the same like vertical alignment. Then our 100 nano is filtering that input, right? Gotcha. Why do I have? This is the opposite to what I want. I don't want that 100 microfarad there. I don't want to copy it. I want to delete it. And then move all of this over so it sort of aligns a little more. Then I want another 100 microfarad capacitor there. Cool, that's good. And then I can mirror this layout, and that's going to give me good, input decoupling and then also output stability capacitor options. All right. There we go. Cool. That's going over onto this side, although I've got these flipped around because our raw voltage goes there. All right, then that's going on. That's the one that's going nice and close to this regulator. Cool. And then I'll sort of just make sure to mirror the layouts fairly well. That looks pretty good to me. And then our power input's going to be here with that decoupling capacitor nice and close. I mean, a bit more space just to allow the big electrolytics, enough space for the hot air to get in there and reflow properly. Yeah, that's looking pretty good to me. We don't need that bulk reservoir capacitor on here because that would be feeding the input stage there, and we've already got that capacitor there, so we don't really need that. But that's looking pretty nice, I have to say. Cool. We'll save that. And then again, I'm just going to export that as a 3D model so I can get a sense of how it's all actually coming together rather than just a bit of a hodgepodge jumble. Yeah, this is getting pretty close to done in terms of the layout, and then the routing is actually going to be pretty quick. I often find that the layout is what really takes a while, and then the actual routing is a fairly quick job. Yeah, looks pretty nice. That's looking good. Sure. That just needs to be laid out there. How are we doing for time? I'll probably go till 10:30. I'd say then that's 2 hours. That's a good chunk. I've got to get assembling bridge 6s and MIDI through gizmos and all sorts of other fun things and shipping some orders out. So let's go ahead and look at our DAC. So we've got 5 channels. So it's basically going to be the same thing duplicated 5 times. So I'm going to start with 1, get a nice sort of layout going around one of the ICs, and then we'll go on and do the other channels. So 24, 23, so basically 21, 2, 3, 4, and then C 43, 45, 46. Cool. So I'll move 21. I'm just going to put it here in sort of abstract space. 22, 23, 24. What was the name of our capacitors? So 43, and then we've also got Q1 and IC. IC1? Yeah, sure. So I'll move Q1, move C43, move C44, and move C45. All right, then IC1 can be routing around this. So the way I've done it, if you look here, because there's 2 op-amp stages, is I've used tried to use sort of A and B both sides, and then D and C to make it as easy to kind of lay out as possible. We'll see how that goes. So this are 23, 24, and Q1 form our voltage level shifter here, which is sort of the input to this PWM to analog conversion. So they're going to go there. Lovely. Then what do we have next? Then we feed into this op-amp stage. That feedback capacitor needs to go right up along those capacitor pins with R22 as the output. So where's that? Should be a low value capacitor there. Yeah, 220p's. Oh, sorry, it's C43, 45, and 46, not 44. So move C46. That's going to basically go, sort of something like that. Sure, then R22 is coming out of there. Okay, so it's coming on the output. It's probably going to have to go next to that. Connect to there. Then we've got another cap there, forming our Salem key filter. 21, and a lot of this, it's just sort of moving things around, playing around with different layouts, seeing what works, what doesn't. Seeing it's a lot of just sort of trial and error placement, to be perfectly honest with you. Sort of feel like that might. Yeah, I feel like that might play a little better. Then I can just go boop, boop, boop. Nice. I tend to mutter to myself a lot when I'm doing PCB layout as well, so don't mind me. C43 is going to ground from pin 5 of our op amp. Well, there we go. That just connects to there. Just give me 1 second. All right. Welcome. I've just jumped in there. I'm kind of getting to the back end of the stream, but we're doing some laying out our, I'm calling it a DAC because it's about getting a PWM from the microcontroller, and then we're really just doing some clever filtering. It's not a typical DAC, but that's the function it's performing, is digital to analog conversion. So yeah, C45. It's going a bit trickier to route there, but maybe we just sort of put it together up there like that, and you get this nice sort of symmetrical little block fed by our level shifting here. That could be pretty good. And then is that our it's our decoupling, isn't it? So we'll put that maybe there somewhere, nice and close to that op amp. Cool. All right, I'm gonna take all of that and rotate it. Find it a bit easier to work in that orientation. Can move that a bit closer. Cool. Then where's this being sort of fed from? That, I mean, that's coming from our microcontroller, so it would make sense to do something like that. Have our input pull-up resistor. These are both pull-up resistors here. How do we do this? Maybe something like that. Then that can just kind of drop down there. 5 volts can go to there. It's shaping up quite nicely. Okay. And put him there. All right. Lovely. So we'll go ahead and duplicate this again. Once again, R25, 6, 7, 8, and then C 47, 48, 49. All right, so move C48, 47, and 9. Then we have move 25. 26, 7, and 8, as well as Q2, which is just here. And I'm basically just going to mirror this layout on the other side of this op amp here. So 27 and 28, I believe, are the level shifter resistors here. So along with that transistor, they're going to go. What's that one? Yeah, I'm literally going to try and mirror this layout here, because I think it's nice and compact and it works quite well. Makes a lot of sense. go there, then it'll go there. Just give it a little bit of space. Cool. Then our feedback resistor goes rotated, I believe, like that. Oh, actually, it's like that. Hang on. How did I? Okay, right. So yeah, that looks right. Cool. I'm just tripping out live. No. Wife is going to work. Why are they not level? Oh, because that resistor, yeah, that's not snapped to the grid. Always snap to the grid. There we go. Okay, so that DAC out one, it goes like that. Then I've got this resistor, which goes, the 5K goes. I'm just basically, copying this and sort of mirroring it up here as best as I can. Then that 100 nanofarads will sit there. Then we've got that 100 nanofarad, which, that resistor, which goes in there, and that will slot in there. And now we've got this, nice kind of easy to route layout that's going to perform really well. Everything's nice and close to where it needs to go. We can just copy and paste this. So that's probably going, might as well, I was going to say we'll end it, but 18 minutes left. We'll keep going and I can plow on and get this done. C44 was from something else, wasn't it? Okay. Well, now do the exact same thing. We'll sort in submodules. I'll go through this a little bit quicker for the sake of getting it done. So 29. So lovely. 47, 48, 49. Oh, hang on. 47 was... Oh, I was looking at the wrong one. My bad. I need 50, 51, 52. Q3. That's going to be on that side. And moving down to channel 4. So we've got 33, 34, 35, 36. Capacitors are 54, 3, 4, and 5, and then Q4. Q4. All right. Sweet. Go ahead and get that routed. Where is the... hang on a minute. 59. Is that the decoupling capacitor? Oh, that's the one for the pots. Yeah, so I missed that decoupling capacitor for this op amp here. So go ahead and sort of center our design around that. Fantastic. So once again, we'll start with that feedback resistor, which goes like so. Cool. And then that's kind of like a reference for the position of everything else. We've got our level shifting going on there. And we've got, that's going to go there. Lovely. Had a bit more space around that, didn't we? Cool. And finish it off. Now, where's the exact? So that was a bit closer down, wasn't it? Something like that. Yeah, sweet. Oh, they won't snap to grid. Always snap to grid. Fantastic. Now, once again, we're just going to copy and paste our layout. Should be getting the layout of this pretty well memorized by now. Did I? Yeah, I was going to say, I didn't think I put those resistors quite so close butting up against there, which means that has, yeah, that's now right. Fantastic. So level shifting resistors go like that. And like that. A little bit repetitive work here, but you know, that's a lot of PCB layout is, you know, a lot of it is just very repetitive. Same thing. Oh, that, okay, yep, that goes up there. And go there. All right, well, that's looking pretty good to me. I can probably move these transistors up a little bit, actually, just to give them a bit more space from everything else. You know, ideally, you want to give your components as much space as practical because it's going to make your not only your routing but the assembly easier. With just makes everything easier if you give them a, you know, as much space as possible. Cool. So that's 4 of our channels done. Then we're only using half of this op amp here, so it doesn't matter quite as much. But for the sake of completeness, we'll follow the exact same approach. What's C44? What's C44 from? Oh, again, that's decoupling from that. ADC, somehow it just keeps finding its way back here. Sorry, little guy. Back you go. All right. We'll bring these up here. So, our op amp decoupling. Level shifters, you guys get the idea by now. Level shifting resistors go there. That's not a level shifting resistor though. Come on. There we go. Goes there. Feedback resistor goes there. Up one. Resistor goes there. Goes there. It goes there, and it goes there. Beautiful. Now we have this nice kind of, you know, matching layouts that are uniform throughout the whole thing. That's going to be going. That's going to perform really nicely. It's going to be easy to follow, easy to look at what's going on. So fantastic. That decoupling there might get in the way a bit, but let's just see how these blocks slot into a piece of that, because they are quite big. That's the other thing. What I'm going to do is you can make groups of components. So new group, I'm going to call this DAC 1/2, or it's 0/1. Then this is going to be that's my group. How can I create a new group? New group, there we go. DAC was there all along. DAC 2/3. And last but not least, DAC 4. Cool. So now that they're grouped, we can just go move DAC 0/1. We get that whole group there. We don't have to worry about reselecting it or anything like that, which is really nice. So if it goes there, put the other one, probably there. Or if we could fit them all in like that, that'd be nice, but we're not going to get that luxury. And then this way our inputs are kind of nice and close to the top, so we can route that quite cleanly, more cleanly than I thought we were going to, but that's just having one look at that, it's going to be too close to our crystal oscillator. We want to keep that far away. That's probably going to be just enough space, I think. Then let's move our second block. How much room do we need? Oh, okay, so that's actually going to fit in pretty well. We could do something like that, for example, and then put our little half block here, there, let's say. That's going to work pretty well. All right, so again, I just want to, now that all the components are on the board, let's push that into 3-dimensional space and see how everything looks. It's going to give us a better idea of, the layout of those little DAC modules, and yeah, we'll quickly see if we've goofed anything up. Wait for it to generate. There we go. Cool. So they look quite tidy indeed, especially once we've cleaned the silk screen up on them. I'm really happy with that. I think that's obviously, haven't put those decoupling capacitors right where they need to go. Might do that now because they're the only things that aren't actually, at least more or less placed. What I am going to want to do is change the channels of these, like which channels they're going into, so that they're not crossing over, and make that layout a whole bunch easier. But our decoupling, we've got these two sort of sections. We've got the digital side and the analog side. So we're decoupling our reference, voltage reference, and then we're decoupling our digital supply voltage. So see 42 and 44 need to be near V16 and pin 9, so I'd deground. So where are 42 and 44, there we go. So which is, it's kind of a annoying layout, really. Sorry, an annoying pinout. What's 15? That's 15 is our VREF. So they're right next to each other. That's really crappy. I really don't like that pinout. We might have to move this whole thing up a little bit so that we've got enough room to place those there. Yeah. Don't have to worry about this being close to the switch for reflow because it's going to be, it's a through-hole part, so it's going to be hand soldered, which is fine. But we're going to have to do that, and then keep that 10 microfarad as close to the pin as possible, as we were talking about before. Yeah, I'd say we'll have to do something like that. I'm gonna move this over, and then again, I already have it selected. Move this up a bit and out that way. Just give it some breathing room. That's better. Cool. Well, we'll save that, and I think we might call it there. That's pretty happy with the progress on this now. This is ready to route. So next week, I'd say in that same time slot, we'll get this whole board routed out. And then we can get ready to send it off and get a prototype. So thanks for tuning in on the stream today. It's great to have you guys. Thanks for saying hi, Brad, and letting us know about your project. if you're interested, I'll pop that link up again quickly. Go and check out this GitHub from Dan. He's a great one of our members in the Pirate MIDI user group, and he's made his own bypass looper and MIDI controller all in one. I've seen this project a little while back, and it's really good. If you want to get a bit of an insight into that, go and take a look. But that's all for now. So bye-bye, and I'll see you next week or around the social media.